Alright, in this video we're going to take a look at finding the probabilities of dependent events. And in previous videos we looked at independent events where the outcome of the first has no impact on the outcome of the second. And then in our last video we took a look at conditional probabilities, which is calculating probability based on an event already happening. And related to conditional probability is the probability of dependent events. So two events are dependent if the outcome of the second is affected by the first one happening. So independent, the outcome of the second was not affected. With dependent, the outcome is affected. So therein lies the difference between independent and dependent events. So dependent events are going to utilize the conditional probability that we talked about in the last video, where now instead of the probability of A and B happening is just the probability of A times the probability of B. With dependent events, the probability of A and B happening is going to equal the probability of event A times the probability of event B, but the probability of event B based on event A actually happening, or probability of event B given that event A actually happens. So when we're calculating dependent probabilities, we are under the assumption that the first event did happen, and that is going to have an impact on the second event. So note that when selecting items from a collection, dependent events often contain selections made without replacement. So we draw a marble out of the jar, we do not put it back, and then we draw another one. So now the number of marbles has changed if we don't put it back, which is going to impact the second event's chances of happening. So example 5, you're dealt a card from a standard deck, and then you are dealt another card without replacement, as usually is the case. Find the probability that the first card is an ace, and then the second card is a 10. So again, these when you're dealt cards, playing a game of cards, you don't get a card and then look at it, take note of what it is, and then give it back. You hold on to that card at least until the dealing's over. So the first card is an ace, and then the second card is a 10. So our first card is an ace, and the second card is a 10. So the chances that we get an ace and then a 10 are going to be the probability of getting an ace, and then multiply that by the probability of getting a 10, given that our first card was an ace. So let's see, for our first event, the probability of getting an ace, there's 4 aces out of the 52 cards. So we have 4 out of 52. And now, assuming the first event happened, assuming we got an ace the first time around, our probability of drawing a 10, well, there's 4 10s in the deck. But because we did not put that first card back, and again, there is only one card that we're getting for the first card we're getting. Now we have one less card in the deck, so instead of 52 cards, there's now 51 cards. So the probability now of getting a 10, given that our first card was an ace, we have 4 10s out of, there are 51 cards left in the deck. There's not 48. We didn't get 4 aces. We were only dealt 1 card. So there's only 51 cards now in the deck. And then when we multiply this out, we get about 4 out of 663, which is about 3/5 of 1% chance of that happening, or 0.603%. So pretty low. All right, part B, we have the first card is an ace, and then the second card is an ace. So we're dealt 2 aces. So the probability that the first card is an ace times the probability that the second card is an ace, given that our first card was an ace. Well, for our first event, we have a 4 out of 52 chance again. And now when calculating the second event, this probability of getting this ace, well, there's one less ace in the deck since we were dealt one already. So now we only have 3 aces left. And because we didn't put that first card back, again, we have 51 cards in the deck, not 52. So our chances of getting a second ace dealt to us are now 3 aces out of the 51 cards remaining in the deck. So when we calculate this probability, we get 1 out of 221, which is 0.452%. So a little bit less than 0.5% chance of getting 2 aces dealt to us. All right, so in our previous video, we looked at conditional probability, and in our formula for dependent events, again, is the probability of event A and event B occurring is the probability of event A times the probability of event B, given that event A has already happened. So if we have this conditional probability here, the probability of event B, given that A has already happened, we can find this probability by dividing both sides by the probability of A. So we're solving this right-hand side for this probability. So if we divide both sides by the probability of event A, we get our formula for conditional probability, that the probability of event B, given that event A has already happened, is the probability of A and event B happening divided by the probability of event A happening. So for tabular data, when finding and probabilities, we're going to look for the intersection of a row and a column. So two rows, likewise, if we have two columns, are never going to intersect, so their probabilities would be considered mutually exclusive. So we're going to go back to our cars table here and look at some dependent events. So example 6, the table below lists the types of cars. So it's the exact same table, exact same numbers. So hopefully you still have that table from the last video. And if a car is randomly selected, so notice now we're not specifying that the car has to be a certain type, import or domestic, or it has to be a certain age. It just says a car is randomly selected. So we're not specifying a particular type of car. What is the probability that it is a 6 to 10-year-old import? So we want to find the probability that it is 6 to 10 years old and a foreign car, which is 12 out of 200. So 6 to 10 years old, this row or this column, and the import row, we have 12 of those cars out of the 200 total possible cars. Again, the total, we just have a car. We're not specifying a particular type in this case, so we're going to use the total number of cars in the lot, which is 200. So we have 12 out of 200, which reduces to 3/50ths. Now, to kind of justify the probability of event A and B, as we looked at in the last formula, the probability that it's 6 to 10 years old in an import is the probability that it's 6 to 10 years old times the probability that's an import given that it's 6 to 10 years old. So we had the probability that is between 6 to 10 years old. There's 23 cars on the lot that are between 6 to 10 years old out of the 200 total. Now the probability that is an imported car based on the total of 6 to 10 years old, well, given that it's 6 to 10 years old, so there's 23 of those cars, and 12 of those cars are imported, so we'd multiply it by 12 out of 23. These 23s are going to cancel each other out, giving us 12 out of 200, or 3/50ths, so 6%. So in terms of why we look at the intersection of the row and the column, and we could just go from looking at the intersection of the row and column, that 12 value out of the total, this is the reason why. So this kind of gives our justification behind why we look at the intersection of a row and a column. So if you were wondering, here's the reason why. If you weren't wondering, then don't worry about it. All right, part B, another car is just randomly selected. So out of the 200 cars we have available, what are the chances it is a domestic car that is between 0 to 2 years old? So out of the 200 cars, domestic and 0 to 2, that intersection of this row and this column, there's 35 of those cars. So 35 out of 200 reduces to 7 out of 40. So whatever percentage that happens to be. About 17.5%. All right, part C, we have cars randomly selected. So out of the 200 cars, what is the probability that it is 0 to 2 and 6 to 10 years old? So 0 to 2, this column, 6 to 10, this column. Well, as we said, that if we have two rows or two columns we're looking at, those events are going to be mutually exclusive. A car cannot be both 0 to 2 years old and 6 to 10 years old at the same time. So the probability of selecting one that is both is 0. They're mutually exclusive events. This is a 0% chance of happening. So it'd be like selecting an imported and domestic car. Well, it can't be both. So it can't be 0 to 2 and 6 to 10 years old. So the probability of that happening is 0. So, all right, that about does it for this video. Thank you for watching, and I will see you next time.